Hello, my name is Mariotte Bottle and I'm going to present the report for experiment 1. As an abstract of this work, we studied the functioning of the Mariotte bottle with a constant emptying flow and a non-constant flow in order to calculate the velocity at which the bottle is emptied. For this, we have to measure the height of the water level, and we have to measure it every 5 seconds until the flow stops. With the help of some equation as a continuity equation and velocity, we found that the initial average velocity is minus 0.001347 meters per second, and the exit average velocity is minus 0.4125 meters per second. So, as we mentioned before, it was studied the Mariotte bottle, so we can find out the velocity. And we also have to apply the uncertainties and error propagation and some descriptive statistics. So we consider that studying this experiment and applying these topics is relevant because it is helpful to develop a more complete and formal report in the future and in the professional life. It is also important to study this type of phenomena and their explanations so we can have a better understanding of these everyday situations and also for applying these kind of problems for solving them in future or in the professional life. So to begin, we have to see what is the Mariotte bottle. So the Mariotte bottle is a device that enables the pressure under which a liquid flows out of our orifice to keep constant for an appreciable time. We can say that it allows delivering a liquid at a constant and adjustable pressure. It only applies if the liquid stays above of the bottom of the atmospheric tube and determines the exit pressure. So next is the theoretical framework. It is important to know some key things for a better understanding. At first, it is the flow. The flow is defined as the quantity of fluid that, whether it is a gas or a liquid, in this case, that passes a point per unit of time. The equation is the flow equals the quantity over time. The pressure can be defined as the normal force exerted by a fluid or gas per unit of area. Because we're measuring force in area, we have that its units in the international system is the newtons per meter per meter square or the Pascal. The velocity, it is a vectorial function that depends on the time and is defined starting of the position because it is the derivative of the position. So we can say that also the velocity can be positive if it increases or negative if it decreases. 0 if the position reaches its maximum or minimum scope. The equation can be seen as limit when times or delta times is tends to 0, or this can be expressed as the derivative of the position depending on the time, or a simple way is the position over the time. The Bernoulli's equation states that the static pressure in the flow plus the dynamic pressure of 1/2 of the density times the velocity square is equal to the constant throughout the flow. So we have this equation to represent the Bernoulli's equation. The kinetic energy, on the other half, is the capacity that the body has to do work by virtue of its movement. So this can be represented with the following equation, which is 1/2 of the mass times the square velocity. an important thing to know is the volumetric flow rate, and is defined as the volume of the fluid that flows through a transversal section per unit of time. This can be represented by Q, and this is the equation that defines it. This shows a derivative that depends on the time, but also in a simpler way can be seen as the velocity times the area of the section. And finally, we have the continuity equation, which is, it says that the that in a conduct, it doesn't matter if section, as long as it doesn't exceed the duration, the amount of fluid that enters at one of the ends must come out at the other. So the fluid is conserved through a pipe. So we can see as the following equation, which is the Q1, or the flow that enters, is equal to the flow that exits. And when using the volumetric flow rate equation, it is like this. The velocity 1 times the area 1 is equal to the velocity 2 times the area 2. So for the development of this experiment, we have to use this equipment and materials, which is a cylindrical plastic container, an atmospheric tube, which is a straw or a PVC tube, a drain tube, also we can use a straw or a PVC tube, a rubble seal or something to seal the top and the bottom of the bottle, marker, scissors, ruler, flexometer, stopwatch, computer, etc. Here we have the figure, which is our bottle that contains the atmospheric pressure tube, the drain tube, the clear plastic bottle, a flexometer, a ruler in this case, and a bucket. Here we have a schematic diagram which shows which measurements were taken into consideration: the diameter of the bottle, the diameter of the tube, the height of the bottom of the atmospheric tube to the reference level, and also the height of the water level to the reference level. Then we have some measurements that were taken. These were taken every 5 seconds with the help of a ruler. After this, we have to report our data in these tables. The first one is the measurements of the bottle. The second one is the measurements of the water level, that were 5 measurements. And with these, we can calculate the areas. So the procedure to make the calculation of the areas is the following. We have the data of the bottle, the equation of the area, the diameter of the bottle. In this case, we're calculating the area in, and we calculate the radio by dividing it by 2, then calculate the uncertainty of the diameter. That is this 5 times 10 to the minus 4. And then we have the radio uncertainty, which is the radio times or minus, no, plus minus the uncertainty that we calculate. Then for the calculation of the area, we're using this equation. Then we calculate the percentage uncertainty of the area. For this, because we're having a potential, we have to take this potential and put it here below and multiply it by the percentage uncertainty of the radio, which we calculated like this. We have 2 times the percentage uncertainty of the radio times 100, and we obtain 1.97%. So then we apply our area equation, and this is the result given. And then we use our rule of uncertainties, and this is the area of the bottle. For the area out of the drain tube, we only change the diameter of the drain tube, and we do the same procedure that it's calculating the radio, the uncertainty of the diameter, and then we put it together. So we have the radio uncertainty, then we calculate the area by calculating the percentage uncertainty of the area and multiply, well, and this is equal to 2 times the percentage area of percentage uncertainty of the radio. So we have the 33%. Then we have to put this together. When we calculate the area, then we have the uncertainty. And using the uncertainties rule, we have this result. After this, we have the table 4, which is a calculation of the average height and velocities with its uncertainties. And for calculating these velocities and its uncertainties, we first have to calculate the height and the uncertainties of height and time. So we have, we take the minimum scale of the chronometer, which is 1 second. So we have 0.005 seconds. Then we calculate the percentage error by using like this little equation. After that, we put that beside, and we calculate the percentage error of the height using the first value of our table plus the second value divided by the previous value. It will be the first value minus the following value times 100. So for calculating the velocities, we have to make a subtraction of the previous height, the first one, minus the next height between the number of repetitions of the measurements that were made in this experiment. After that, we have to calculate its uncertainty. So we calculate the uncertainty, well, the percentage error of it by taking the percentage error of the time and the percentage error of the height. So we have the following procedure. Well, first we calculate the percentage error of the initial velocity. Then we calculate the percentage, well, how much it represents of this percentage, which we multiply it by, well, the value of the velocity, of the initial velocity, times the percentage error of this velocity, and this divided by 100. And well, for the final steps is to calculate the velocity out, which we are using the continuity equation. So we solve it for the velocity out, and we have this equation. Once we obtain this, we have to calculate its uncertainty, so the percentage error of this velocity, and how much it represents of this quantity. Well, how much it represents this percentage of this quantity. So we have to apply the propagation of uncertainties, which is this rule. It is the square root of the different percentage uncertainties of the area in squared, plus the percentage of the velocity in squared, and finally the percentage error of the area out, and also it is squared. Then we only calculate the value of this percentage, and we have to multiply the velocity out, the value of the velocity or the average velocity out, times the value of the percentage error of the velocity out divided by 100. Finally, we can make our graphics, our graphs, which is the average time on the time t, and the velocity, the average velocity of the water on time t. As this, once we obtain this, we can see, or we can analyze that the first, the figure 4, it looks very uniform, and it can be said that it looks at what was expected to look. On the contrary, the figure 5, it is more dispersed, and it doesn't look as expected graphic with a uniform beginning, because it is above the bottom of the pressure tube, and eventually it decreases the velocity when it's below the pressure tube. But if we analyze it a little bit more, we can see that it is uniform at some point at the beginning, as it is stated in this experiment, and then it goes, or it decreases in this case because our velocities are negative, it decreases and it goes to zero. In addition, the discrepancies are very large in the second, well, in the figure number five. So this might indicate that the results are not as accurate and reliable as if they had a small discrepancy. Likewise, it is relevant to see that the initial velocity, well, remains with our data of the tables. The initial velocity remains constant, and also it is less than the final speed as it is stated or it is expected. It can be due to the fact that the calculated area from the initial velocity is much greater than the final velocity one. It may help us to verify that the continuity equation is being fulfilled in this experiment. It can be also considered that the main measurements errors that could affect the results of these experiments were mostly systematic and random. With the systematic errors, it is possible to see that some of the measurement instruments, such as the cell phone timer, were not precise, since there were some failures and slowness. And in the same way, there was a random error because at the time of taking the heights, it depended a lot on the angle of the person that were taking them, because it could vary a lot, and also the ruler was not the most precise instrument to use. So we suggest to best perform this experiment and obtain these more accurate and reliable measurements. It's important to consider the shape of the bottle. It may be easier if it's more uniform. As well, to make it easier, it is recommended to have two or more people helping to recapture the data, so we can avoid distractions or to reduce these measurement errors. To conclude, we can say that in this work, as it was said in the abstract and the very beginning, we wanted to measure the velocity at which the bottle is emptied using the Mariotte bottle that has a constant emptying flow and non-constant flow, in order to obtain these several measurements of the height of the water level, so we can have or calculate our initial average velocity and then our exit average velocity, which were 0.001347 meters per second, and the final velocity 0.4125 meters per second. This is important. This knowledge is important since it shows us that the results that we obtain are close to or similar to what would be expected in this type of experiment. Likewise, it is important also to highlight that it helps us to understand the physical phenomena in detail and apply our knowledge acquired in this experiment to solve problems of our daily life. It can be said that one limitation could be in the part of the measurement instruments, since the scale was very limited. And for further studies, it remains to determine the pressure exerted by the atmospheric pressure tube to analyze it, and if it is similar or almost the same value of the atmospheric pressure, and also how it affects the velocity and how the velocity changes with this. Thank you.